Hi everyone, my name is Manveer Sidhu. Today I'm going to present a presentation on a topic carbon nanotube field effect transistors, also known as CNFET. Here is the outline of the topics that I'm going to cover in my presentation. So let's get started. First of all, the introduction to the topic. In today's world, the speed of every electronic device is increasing, for which the size of transistors which are embedded on the integrated circuits are getting reduced. Silicon is most widely used material in building these transistors on the chip. But with the reduction of size of these transistors, the silicon transistors start facing various problems like lower threshold voltage, higher gate current leakage, and lower channel mobility. The properties of the carbon nanotube like high drive current, large transconductance, high temperature resilience, and strong covalent bond makes it as a suitable candidate to replace silicon as a material for building these transistors. So, what are these carbon nanotubes? The carbon nanotubes were first discovered in Japan in 1991. These carbon nanotubes can be thought as the rolled up sheets of graphene. The electrical properties of these carbon nanotubes depends upon its different type of patterns that are available in these carbon nanotubes, which are zigzag, armchair, and chiral. The working principle of carbon nanotube field effect transistor. The basic principle of these FETs is same as MOSFET, where carriers are supplied by the source terminal through the channel and drain terminal will collect these carriers. The gate terminal controls the formation of this channel. As the gate voltage is more than the threshold voltage of the MOSFET, a channel is formed between the source and drain. The one of the difference between MOSFET and CNTFET is that a channel is made up of carbon nanotubes in the CNTFETs. Types of CNTFET. The carbon nanotube field effect transistors can be classified into two categories based on its geometry and based on its operation. Based on its geometry, it can be subclassified into three categories: the bottom gate, the top gate, the wraparound gate. While based on its operation, it has two subcategories: the Schottky barrier and the MOSFET-like CNTFET. So let's start with the bottom gate. The bottom gate CNTFET was first of the CNTFET that was constructed. These are simple devices fabricated by depositing a single wall carbon nanotube between the source and drain, as we can see in this figure. These CNTs are fabricated by the process of laser ablation. This CNT behaves as a channel between the source and drain and is responsible for the movement of carriers from source to drain. What the drawbacks of this bottom gate CNTFET? First of all, it can be observed that it offers low transconductance as compared to other CNTFET, which reduces the bandwidth of the operation for any type of operational amplifier made up of this transistor, and also increases the noise in the system. It can be observed that it requires high gate voltage to turn these type of bottom gate CNTFET, since their threshold voltage is large and it has no current saturation. The next that type of CNTFET that came up was top gate CNTFET. It was came up generally to improve the device performance as it overcomes the limitations of the bottom gate CNTFET. In this one, a thin top gate dielectric is deposited on the top of a nanotube, e- which is shown over here, either by the process of evaporation or atomic layer deposition. So we can see a gate dielectric is deposited on the carbon nanotube that is connecting the source to the drain. And finally, a top gate contact is deposited on this gate dielectric. So there were certain advantages of using this top gate CNTFET. The first one is that arrays of top gate CNTFET can be fabricated on the same wafer, since the gate contacts are electrically isolated from each other. So we can fabricate set number of top gate CNTFET on a single wafer, which is certainly a huge advantage, as you can put greater number of transistors on a single wafer, which reduces the cost of fabrication. And this feature was not available in backgate CNTFET. It can be seen that a lower gate voltage is required to start the operation of top gate CNTFET as compared to the backgate one, as the large electric field can be created in the channel at lower voltage. The next type of CNTFET that came under this category was wraparound CNTFET. In this type of structure, gating of the entire circumference of the tube is done. In this type of structure, a cylindrical gate is drawn and then it is etched away from its edges, and source and drain is connected at its edges. The clever engineers came up with this idea of changing the shape of gate, as it reduces lot of the limitation that was seen in the previous structures that we have observed so far. So what were the advantages of using this wraparound CNTFET? The first of all, it reduces the leakage current in the device, which is possible due to the geometry of the gate that we were using in this. It improves the device on-off ratio due to the reduction in the leakage current. So we can see, if we are able to reduce the leakage current, there are certainly a lot of advantages that came in our way. This type of gate structure also provides more electrostatic control over the channel. The Schottky barrier CNTFET. It is the first type of CNTFET that came under the based on the operation type category. The Schottky barrier CNTFET works on the principle of direct tunneling through the Schottky barrier at the source channel junction. The barrier width in this is controlled by the gate voltage. As we increase the gate voltage, the barrier between the source and the drain will decrease, and due to which there will be increase in the quantum mechanical tunneling, and more carriers will be able to move from source to drain through the channel. Limitations of Schottky barrier CNTFET. The energy barrier of Schottky barrier limits the transconductance of the CNTFET in the on state, which decreases the drain current and therefore its speed. So speed is one of the limitations of Schottky barrier CNTFET, as they are not as fast as compared to other types of CNTFETs. The Schottky barrier CNTFET have stronger have strong and bipolar attributes. That limits the uses of these devices in conventional CMOS architectures. The another type of CNTFET that came up was MOSFET like CNTFET. As we can observe from its name, that this type of CNTFET must behave like the MOSFET, and it is true. The structure of this device is slightly different than the Schottky barrier CNTFT, since it uses heavily doped terminals instead of metals for source and drain. As you can see, the source and drain in this figure is made up of heavily doped regions, while in the Schottky barrier, the source and drain were made up of metals. This device is formed in order to overcome the problems in Schottky barrier CNTFET. So as this device performs on basically as same as the normal MOSFET, so its principle it operates on the principle of modulation. As more gate voltage is applied, the barrier height will decrease and it will lead to more movement of carriers from source to drain. Advantages of MOSFET like carbon nanotubes. Its source drain channel has no Schottky barrier. As a result, it has considerably higher on current, and consequently this type of CNT-FET are very suitable for ultra high speed performance applications. It is more suitable to use in CMOS technology for building complex circuits like op-amps, inverters, etc. As its properties resembles more with the conventional type of MOSFET and it behaves like that. So now we're going to look at the factors that influence the performance of CNTFET. There are two most important factors that affect operation of CNTFET, which include dielectric and passivation. First of all, we're going to look at the dielectric. Using high dielectric materials can provide efficient charge injection to the channel. And we can also see that providing high gate capacitance using these high dielectric materials causes faster switching of the FETs. Passivation. Passivation is a process that is used to cover up the packaged integrated circuits made up of carbon nanotube due to the following reasons. Nanotube sensitivity. It can be observed that carbon nanotubes are very sensitive to the contaminants, and it highly affects in higher performance digital applications. Due to these contaminants, there is a shift in the threshold voltage among carbon nanotube field effect transistors of the same geometry, which is a limitation for any type of FETs. Now we're going to compare the MOSFET with the carbon nanotube field effect transistor. It can be seen that MOSFET has lower channel mobility as we reduce its channel length, while CNTFET offers higher channel mobility even we reduce its channel length, and which is certainly a big advantage in case of CNTFET. MOSFET has higher threshold voltage, while CNT offers a lower threshold voltage which causes faster switching and lower power dissipation. There's more leakage of power as we reduce the channel length and in the MOSFET, while in CNTFET there is negligible leakage of power as we reduce the channel length. So what does the future hold for the CNTFET? First of the CNFT was well been tested in one of the laboratories at MIT by researchers and scientists on June 1, 2020. It shows that CNTFET can be fabricated at fabs and offers certain advantages like 3D structure of the transistor. Most of the transistors that are built today are 2D. It reduces the cost of production and increases the speed of fabrication of these transistors. But we still have to wait to see how these carbon nanotubes can be used in fabs, as it is hard to handle these carbon nanotubes in atmospheric conditions. which is a limitation for it, and scientists and researchers are working on this thing. Here is list of reference. Here are the list of references that I used to make my presentation. Hope you liked it, and thank you.